Okay, so we just delete the ligand from the com file, which is after running PDB for after running the first command, but sort the PDB and check the file. Okay, so just grab the reg file to the or folder. Okay, so all things is ready to make a topology file. I mentioned that in the previous session that we use TLIP file. We need to create a TLIP file for creating the topology. So because it's need TLIP, TLIP is a helper program that actually help Amber to compare all the information with all these files together. And if all things, when you compare the library of the Amber with the OR files, and if all things is correct, then we could have a successful topology and correct topology. So just let us start using TLIPs. So this is just belongs to Amber force field. We use this force field for making or for the protein. This is a force field named Amber. Amber has various force fields for these. All force fields as could you could use your force field, choose your force field based on your need. For example, if you want to work in a membrane, you could use charm force field and so on. So for this purpose, because our protein has a ligand and metal, and this is the acoustic protein, it's better to use this force field. And also for the water molecules, we use this force field, this GAF, and that's it. Okay. We just load this in Amber in the TLIP environment. For the starting to the TLIP environment, just simply type TLIP and right click all the information, just hit enter to execute. I think this is the information that should be loaded from the Amber library. Yes, it means the Amber has a library for standard residues, that water, and for ion. Yes, okay. So because Amber could not because Amber doesn't have any library for the protonated serine and the ligand, we actually created a library. Yes, so we need to add a library to that TLIP environment to tell Amber, okay, I know that you don't have this library. Yes, but I create a library, so use mine. Okay, all clear?
Yeah.
Okay, so we actually preparing this file. So this first we told Amber, told TLIP, okay, load this file, prepin file. We actually create a prepin file. Yes. Okay, hit enter. Okay, this load. And then we ask them, okay, after loading prepin file, we have farsi mode 2 file. Load this farsi mode 2. Okay, perfect. And we have farsi mode 1, just load it too, because we actually prepared this kind of information so that Amber could be able to create a topology file for this kind. Okay, so move to that one. We have a ligand, or ligand name would be GDP. So we actually prepare this file, farsi mode GDP. Just use that file. Okay, and we load it. Perfect. and we need prep file for GDB. We already create this kind of file, so just we need to upload it in the Amber library. We ask TLib to tell Amber, okay, use that file. So we know, or so after loading all information, you see that Amber could be able to recognize GDP and SEP. So after all this information, except the TEP, this is for another project, so I use the same theory. So now that we loaded all the information required for recognition of the GDP and the SEP, we simply load the GDP file. This is elegant, yes? So we ask TLib, okay, no, you know the parameter needed for GDP and SEP. So now you could load GDP multiplier. And we successfully load that. And then to see if Amber could recognize or file, or based off the information, based off the library that we already made, just check the GDP file for us. Okay, there you go. It's all or parameter. So all the parameter for the GDP unit is loaded, and Amber could use it because it's recognized the charge of that is minus 2.999. It's not completely zero. We know it's not zero. Just this warning is told us this unit is charging. Okay, we know that because we want this unit to be charged. Okay. And then we need to load our receptor. There you go. And then we want to combine, sorry, I just need to delete that because, okay. We need to combine receptor and the PDB. We just ask Amber, so now you have all the information that you need for recognition of all these atoms in my system. So use those and then combine a receptor and ligands. Okay. So now you could load our original PDB that contain all the information for our system. Just combine, okay. So as I mentioned before that we need add counter ion in the previous session. As mentioned that we need add counter ion to neutralize the system. So we need to first charge COM. Okay, or total charge would be that for the system, for the COM. Okay, so then we told TLib, so add counter ion because our charge is minus around -6. So we need a positive charge so that it could change turn the charge to the 0. So in that step, we told that, okay, please add counter ion to the COM until the overall charge gets 0. Okay, perfect. And guys, this charge replacing but by water, not a residue, not a ligand, just water, not even not a crystal water, just the water that Amber actually puts on a box. So after that, we ask Amber to create a box. This is a shape of the box, and fill it with water around. So we just ask Amber to create a box around your system. This is the shape of the shape of the box, and this is the dimension of the box. And we ask Amber to put this type of the water molecule into the box. Having the water in the box is necessary for having a proper dynamic of the acoustic protein. So it's okay. Then we could save our system. This is a topology file. These are the topology file, okay? We just need to save a topology file for them. You could actually put another name for that, but I use always these same things because I really want to all the system for that actually simulate me and Fred have the same name, so you could share files together. So it's much better. Okay, and then it's so you see we have these now. You could recognize that's told us, okay, you have these number of the water in your box, and also you have a ligand and you have a protein too. Just simply quit. You see we don't have any error and notes, just have a warning that told us that your system, you have a ligand that's not zero, and we already know that our ligand is not a zero charge ligand. Okay, so the last thing, if you see, there you go, we have this topology file. The last step that we need to care about is adding magnesium. Yes, with this, we use that one to add the magnesium, and we use that comment for adding magnesium. Okay. This comment literally see that use this in file. This comment as mentioned that use in file. Sorry, just okay. This comment told. Okay. This comment told that use this in file and add magnesium to that file, this topology file, dash b means topology file, okay? And use that program. So we just copy, and you see that it's adding the selected metal ion is Mg. Output topology file is that one. This is the final topology that contains all information about the non-standard residue, about the ligand that already we know that is have a charge -3, and also have a magnesium. So in that part, you done, and you need to create a folder named MD for the final MD and transfer this file to the empty file. For the empty file, you need to have all the information about, just let me, okay. As I mentioned before, that for the MD, you need to do minimization, 3-step minimization, so that you be sure that your system have no clash, okay? And it's minimize your energy too, okay? And this actually care about the heat and density. All things could be converged and do the calibration and the final production run, okay? So each steps need to specific procedure that we prepare it for you. This is a procedure for the okay. So let's start from the main one. This actually told you the step that we use, and the important things that you need to care about is that this should be changed to the number of the residue you have in your system. This would be the fix for acoustic system, I believe, and just need to change that step. Though you don't need to actually know about these information. If you actually really want, you could go to the Amber site and download the manual. This explained all the information in the manual. Just for that step, if you open the COM PDB, you see your starting residue is 1 residue for the protein, not the ligand for water. Okay, and the end one is 72. Yes, 17.2. So just remember that, and you need to have that, because in the MD, in the minimization step, you actually put a restraint on, because before production run, we need to actually prepare, check the energy, check the density, check the temperature, check the pressure, and do all things so that we be sure that we have a correct system, and then put it on the final product or final MD or production MD. Okay, the first thing when you actually create a product topology file, we don't these not the system is not ready yet, because the energy we need to actually minimize the energy and solve the clashes, and you have to have the convergent density, and the temperature would be constant, something like that. Okay, so the system is so sensitive, so we need to add restraint to put the system, get the system stay together and minimize the energy, solve the density, and then remove all the restraint to allow the system to dynamic. This restraint, we need to add this restraint to the on the protein, so that the protein do not move, because the system is so sensitive. If the protein move, okay, the system would be collapsed. So we need to first minimize the energy, care about the density, and constant in and solve and density, and go to the equilibration method, equilibration steps, and then we could remove all these restraint. So if you see we have a restraint here, just guys, be sure that the restraint should be applied on a protein, not a ligand. Okay, so for protein have, so it's okay. And in mine too, we have a restraint too. Okay, and in 3 we don't have any restraint, because we have 2 minimization step, and the first, almost all the clashes is solved, so it's allowed to more movement for the protein. And in density 1, we also have a restraint, because we could apply for restraint. And if you see the production run, there is no restraint. And this is the step that we see that is all the steps. We have that much of the steps. And this is the, if you remember that when I told you about, we talk about how MD is working, I just solving the second law of Newton. Yes, this is actually is that. This is told that, okay, at each point 0.002 step, just solve this equation. and create a new position for each atom. It is literally told that. So then we need to prepare a bash file. As I told you, this is the bash file. So this is bash file related to the Compute Canada. If you want to work on a different server or cluster, for example, if you want to work on a Cedar, Niagara, you need to change this header too. But this is actually for the Compute Canada, for the Graham. And this is the module that we know that we want to simulate our system using that one, that program, that version. And this is the only for all the steps you need to do so that you have the right. So simply, I just put all these together and just copy my directory name and create a new terminal and load this one, just this one, for the creating actual doing the simulation for the preparing the topology. You need to create, you need to actually run this two module, but because you already put this model here, you already put this model here, you don't need to apply that. Yes. So I just simply rename it to the MD. Okay. Just new terminal, cd, we go to the directory, and then s bash md bash file. Okay. Just hit enter, and our job is submit, and my number is that. So if you want to see the status, just simply type SQ. So it's a pending. My account is that, it's a pending. If you want to cancel a job, just cancel. The number job would be 75969972 and hit enter. And if you see, my job is canceled. You see? So any question, guys? So you could practice all these steps. I will send you the command line and the TLIP file. So you could practice that, and after just submit a run or submit a job. After finishing production run, in the next session, we are going to do analyze of file and visualize of file. Yes. So any question?
Not from my side.
Pardon?
Not from my side either. I think I'll watch the video once again and
Yeah, you should actually do
like
it once with your own. So it's yeah. I just want to I just want to go through the steps with you, and you have the video. So when you actually get back to start your own project, for example, I will send you all the information I told you about the prepare the file. So you need to start. I just send you a file. Okay, you need to go through the preparation step and care about all files and PDB, and then starting making a topology file, and then go through the MD. Okay, so you actually get a better understanding about it. I just want to go through this step with you first, so it's actually handle it much more better. Just watch the video again and shadow it, simply shadow it.
okay.
Yeah. And you have my email. Sometimes I am in the lab most of the time, so I have my laptop is my office, so I couldn't check the Slack, and I don't have the Slack on my actually phone. So just email me, okay? If you have any question or something like that, email me. We could set up a meeting to solve the problem if you have.
All right.
Perfect.
Thank you.
No
Thank you.
problem. No problem. So I just process the video and send it to you. Okay?
Okay.
Okay, thank
Perfect.
you.
Have a good one.
Thank you so much. Bye
I'm
bye.
so sorry about the problem that's happened. I have no idea about that. My system is crashing, so sorry for that.
It's fine. Thank you.
No problem at all. Okay, have a good one. See you.